Okay, so you've been given 3 examples at the top. You're supposed to maybe perhaps recognize a relationship using the information that's been given. So if you can generalize the pattern, that would be great. And then once you think you've figured out the pattern, I want you to go ahead and come up here and fill in the blanks. So if you think you know one of them, let's come up and fill in the blanks, and I'll tell you whether you're right or wrong. This should not take 5 minutes to do, so we can get started with the notes. But this is a little introduction to what we're doing next. So are we recognizing a pattern? Nobody recognizes a pattern yet.
I do.
Okay, so go ahead. Do you know any of these answers? Can you come up here and fill in any of these answers? Yeah, go ahead. Fill in something, and maybe using an additional piece of information, other people can actually. Okay, so a 4 there. Anybody else? That is correct. So now you have a 4th example. Using this 4th example, okay, so I'm going to write it here for those people who are in the gym. Okay, do we have another example? Can anybody fill in any of the other blanks? All right. So we're going to keep filling them in until you think you have the answer. 2, that is correct. That is correct. Okay, anybody else? Let's keep looking. Now we have 5 examples. That was beautiful.
The number 3 is 125.
You are absolutely correct. No, they are not making these up. Now you have 6 examples.
Number 4 is 6.
Mm-mm.
No, number 4 is on. Number 4 is on.
No. No. Anybody else? No.
Oh.
I'm thinking I.
Do I have it? I think I actually have it.
Well, tell me what you think you have.
Alright, so tell what I think the rule is.
Oh, you think you have a rule?
Like maybe.
Okay, tell me your proposed rule.
You're going to find what? So the power is the number maybe. It's 5. And then 5 to the power 3 times. I'm looking at number 3.
Number 3.
5 to the power 3 times equals 5. So 2 to the power 4 times is 16. 6
We're 2 to the 4th equals 16. Okay, I agree with you.
And 6 to the power of 2 is 36. 2 to the power of 4 is 16.
Oh.
So 4B.
So what would number 4 be?
Yeah, that's why I don't know.
I'm sorry? No.
Maybe -1?
No.
2 to the power of -1.
It would be I.
It'd be -2.
Y'all are pitiful.
-2.
2 to the -1 using your rule is what?
1/2.
1. Oh, thank you so much. 1/2. Can we do number 5? Anybody think they have number 5?
1/100.
Number 5?
Oh wait, no.
-10.
What?
Negative.
No. Yes, it is -3. 10 to the -3rd is 1 over 10 to the 3rd.
Number 6 is 9.
Number 6 is 9, because 9 squared equals 81. And last but not least, what is the fill in the blank? It is 3. Okay, now I gave this to you in this format because the next family of functions that we're going to work with, this term seems to cause a lot of trouble with people. So I thought before we introduce that term, let's go ahead and do a super fun puzzle. Maybe recognize a relationship. So for each of these, if I were to rewrite this statement, this equation, as an exponential equation, you said it would be 2 cubed equals 8. What would the next one be? Okay, and the next one?
16.
That's right. And remember, we can rewrite this as the square root of 16 cubed, right? So we can go back and forth among the algebra, using the algebra. Now, this little example set here is leading us into the next type of functions. So let's go ahead and talk about this next type of function. The next family of functions, that we are working with thank you very much, are logarithmic functions. So what is a logarithm? Well, if I'm working with a logarithm, that is just an exponent. So if you noticed, I gave you some examples that were written in a very specific form. The form that we saw was power, little base 3, let's say of 81 equals 4. If I wanted to rewrite that in exponential form, it was this. So that was from the previous fun puzzle. So if I'm looking at this, let's go ahead and formalize what it means to go from, let's say, logarithmic form, so a form that's represented in terms of logarithms, and exponential form, where we have a base raised to a power. So if I'm looking at converting something from, let's say, a logarithmic form to exponential form, if I see something that looks like this, I know that my logarithm, the result of taking the logarithm of something, is an exponent. My output, y, is the exponent. Now, how do I read the right-hand side of that logarithmic equation? I'd see log, which is the abbreviation for logarithm. This little b, this little subscript, is a base. And then my input to my logarithmic function, also known as my argument. Oh, come on. My argument is also my input. Okay? So I would read this as y equals log base b of x. Now, I can convert that. Instead of the word log, I can have the word power. So I could have log, which is an exponent, aka a power. So instead of power base 3 of 81, I could say log base 3 of 81. So that is this logarithmic form, log with a base, a little subscript of an input. I can convert that, just like you noticed with those examples, to exponential form, where I take this little base b, that becomes the base, that we raise the exponent to, and that's going to equal the argument. So we have to be comfortable going from logarithmic form to exponential form and vice versa. So let's look at a few examples. So again, in this first form, this is logarithmic form, I have y, which is my power, my output, equals log base b of x. In exponential form, that would be b to the y equals x. Now, some people feel more comfortable with one form going to the other, but we should be able to go back and forth. So if I look at this exponential form, can I rewrite it in logarithmic form? So the first one, this first example, would be what? Log base 2 of, that's right, because 2 to the 5th equals 32. Does that make sense? Yes? Okay. Now, let's go ahead and try the next one. How would I represent this exponential equation in logarithmic form? It would be log base. What is the base?
Yeah, 12.
The base is the base. So the base of the exponential form is the base of the logarithm. Okay, and that is going to equal of what? Oops.
1 over
1 over 125 equals -3. Okay, what about the next one? Can I take the logarithmic form and represent it in exponential form?
Yes.
Okay, how would I write that in exponential form? Okay, again, the base is the base. The base of the exponent is also the base of the logarithm. The output is the exponent. Okay, what about the next one? How would I write that in exponential form? Ooh, I don't see a base here. What happens if I don't see a base here? If you don't see a base there, it is base 10. We live in the world of base 10. So if you do not see a base written there, just like with square roots, if you don't see a root index, we know it to be 2. If you have a logarithm that has no base represented, it is base 10. This is known as a common log. It is the log that if you see that log button on your calculator, there's a log button, is base 10. Yes.
What is the significance of this?
Well, if you think of money, our units of measures, centimeters, millimeters, right? Everything is base 10, right? So ones, tens, hundreds, thousands place. 1/10, hundredths, thousandths place. So we live in the world of base 10, right? Soon as we get to that, we move to the next decimal place. So that's what we live in the world of base 10. Okay, so now knowing what I know, when I see log, when I see log of an input, that's the same thing as log base 10 of an input. These mean the same thing. If I don't see the 10, I know it to be there. So now I can rewrite this as log base 10 of 1 over 100 equals -2. So if I were to rewrite that in exponential form, what would it be? And do you see why that is true? Okay, so now we can formalize it, right? Just like we said here, we can formalize that, and you must know that relationship. That relationship is key. We have to be able to go back and forth. All right, so let's go ahead and see if we can evaluate some logarithms using the information that we know, that relationship. So I'm going to go ahead and rewrite that relationship. So y equals log base a of x. I can put anything here, right? I can use y or a or x, but since we're used to this, then this would imply in exponential form, what? Can you remind me? Base is, if I'm rewriting this logarithmic equation in exponential form, the base is a raised to what power? Y, right? Because the output to a logarithmic function is an exponent. A logarithm is an exponent equals x. So we need to know this relationship. All right. Keeping that in mind, there's shortcuts. So there's a couple of different ways I can approach evaluating these logarithms. I could, if I wanted to, set each of these equal to x, rewrite it in exponential form, and just kind of figure out what x is. So let's try that in the first example. So if I were to set that equal to x, because that's what I'm trying to figure out, what that equals. Can I rewrite this in exponential form? What would it be? The base, well, let's rewrite it in exponential form for practice. That's right. So therefore, that would imply x equals 4. Isn't that true? So that first one equals 4. Now, could I have rewritten for kicks 16 another way? Maybe with the base 2, just for kicks. Just think, let's think of it in another way. Is 2 to some power 16? Isn't 2 to the 4th 16? So can't I rewrite this as this? And then we said the answer was 4. Interesting. All right. Well, let's go about the next one by, let's first just see if we can rewrite it in exponential form. So this logarithmic equation written in exponential form would be what? Well, no log.
7 to the y
Well, to the x.
to the x equals 1 over 4.
Okay. So what would x equal? X, I'm sorry? -2. Could I have rewritten this? Well, since the base of that logarithm is 7, could I rewrite that 1 over 49 as 7 to some power? Yes. Oh. Oops. Isn't that interesting? All right. Well, let's go ahead and take the next one and see if you want to rewrite it in exponential form, you can. You don't have to. If you did, what would it be? 25 to the x power equals 5. Ooh. So what would that imply x equals here? 1/2. And what about the next one? If I were to rewrite the next one in exponential form, what would it be? The 5th root of 2. Yes. Now that's kind of ugly here, so let me fix that. Now, this example looks weird. So maybe I want to rewrite this as 2 to some power. What would that power be? 1/5 power. So if I have my bases being the same as they are here, these bases are the same, then I can set the exponents equal to each other. So that means x equals 1/5. So this equals 1/5, this equals 1/2, this equals -2, this equals 4. So I could convert it to exponential form, or maybe I could rewrite it where the base of the exponent is the same as the base of the logarithm. Why you might want to see if you can rewrite it in this form is because there's a beautiful property. A property that states, well, if I have this, I know that my 2 exponents are equal. I also know that b to the 0, as long as b is not equal to 0, and I should say if and only if b is not equal to 0, that anything other than 0 raised to the 0 power is 1. So if I keep those pieces of information, I can interpret this using logarithms. So if I were to rewrite this, this would be log base b of b to the first equals 1. Do you see how this means the same thing as that? Knowing the relationship, right? Because I could take this little base, raise it to this little exponent, and that would equal my argument, right? Isn't that true? So if you know that relationship, we have this wonderful little property that states if the base of the logarithm equals the base of the argument, your output is just the exponent. So what does that mean? Let's look at a few examples. For example, if I have log base 4 of 4 cubed, what does that equal? It equals 3. Why? Because the base of the logarithm equals the base of the argument, so your answer is just the exponent. Does that make sense? Okay. What if I give you this? What does this equal? What if I give you this? Okay. So knowing that property helps. The next property, again, utilizes the fact that b, so long as it's not 0, raised to the 0 power equals 1. What does that look like in logarithmic form? Log base b of 1 equals 0. So that means if my argument, if my input to my logarithm is 1, this is big. If the input to the logarithmic function or expression is 1, the answer is always 0. It does not matter what the base is. Why? Because that is telling me for every input to a logarithmic function of 1, the output is always 0. Just like in our parent exponential functions, it always passes through 0, 1. For every parent logarithmic function, it always passes through 1, 0. So what if I gave you this example? What if I gave you log base 3 of 1? What is that? It's always 0. Now, as I mentioned earlier, we have something known as common logarithms. Common logarithms are just logarithms with base 10. Common logs. So if I give you log of x, I'm really giving you this. I don't have to write the base 10. It is implied. We live in the world of base 10. So a common logarithm is base 10. On your calculator, when you see this button, that means base 10. It doesn't have to have it written down there. So let's see if we can use any of these properties without a calculator to simplify. And again, there's a couple of different ways we can approach these. Let's see how you want to do it. Looking at the first example, how can I rewrite that? Okay, so you want to set it up as an equation and then rewrite it in exponential form. Okay, so 10 to the x equals 100, so x would equal 2. Is there another way I could have written that logarithmic expression? Log base 10, can I rewrite it as 10 to some power? Yeah, it would be 10 to the second power. Do you see that? Either way, what about the next one? What is the next one simplified to? Okay, but again, if you notice, the base of the logarithm equals the base of the argument, so what does this always equal? Okay, what about the next one? It is just 0 because remember, it doesn't matter what the base is of the logarithm. If the argument is 1, the output is always 0. Okay, what about the next one? It just equals 5. Again, we're using the fact that the base of the logarithm equals the base of the argument, so our answer is just the exponent. These can be real fast if you know the properties. Now, can I do the next one using any of my little tricks? No. Does anybody think they have the answer to the next one just for kicks? Does anybody maybe see it, hypothesize what the answer to the next one would be? Does anybody see anything? Maybe the base here is the same as the base of the logarithm. What did you say, Miles? Say it out loud. 90. You are correct. It is what the calculator says. Okay, so how could I represent this differently? Well, I know two things. I know that if the base of the logarithm is equal to the base of the argument, that my answer is just the exponent. I can also then, if I were to rewrite this, see that if I have a base raised to a logarithm with the same base, that my answer is just the argument. So that's where that 90 comes from. 5, we have to use a calculator. So let's go ahead and put this in the calculator, find the log button. Do you see where it is, or do I need to pull up the TI emulator? Find the log button and then enter in 90. So this one is a calculator problem. This one we can't do with any of our beautiful properties. This one we need a calculator. You need to be able to evaluate the ones without a calculator, that if I put this in the calculator, tell me what this equals approximately. 1.954. Why? Because there is no way for us to determine what x is if I look at it in exponential form. So this one is a calculator. These we must know. We have to know those. Now, we said that common logs are logs base 10. What do you think natural logs have as their base? E, the natural number E. We talked about E. And do we remember what E is approximately? 7, yeah, more than 2. You should need to know that it's more than 2. Okay, so if I'm looking at natural logarithms, I'm looking at logarithms with a base E. Now, there is a nice, clean, abbreviated version, another way to represent logarithms that have base E. Logarithms that are base E are natural logarithms, and this log base E can be represented as ln, log naturel. So that's where that comes from. ln, and there's an ln button, it's the second function to your log button on your calculator. That means you are dealing with a natural logarithm. So common log is base 10, natural log is base E. If I give you this notation, you need to be able to realize that I'm dealing with log base E. I'm not going to write log base E. I'm going to write ln, natural log. So this first example here would be natural log of 90. If I put that in the calculator, what is approximately the value of taking the natural log of 90? 4.5. The next one you should be able to do with, you go to the second log, which is ln, and then you type in 90. And then hit enter. Okay, do I need to pull this up? I can pull it up. Are we okay, or do I need to pull it?
It's not the second log.
It's ln underneath, sorry. Yeah. Underneath ln. Do you see it? Oops. Let me just show everybody in case. Okay, so here's the log button. So if I'm taking the log of a number, so I don't know what we did the log of before. 90. So there's the, bless you, the log, oops. Sorry about that. So if I take the log of 90, bless you, there it is. And then if I take the natural log of 90, there it is, right? So 4.5. Now, looking at the next one, you don't need a calculator. You should be able to answer the next one automatically, knowing our properties. Bless you. Can you tell me what the value of the next one is?
No, the base and the argument are the same.
The log of the base equals the log the base equals the base of the logarithm equals the base of the argument. So since these two are the same, it equals just 1. Why? Because e to the first power equals e. Now, am I going to give it to you in that form? No, I'm going to give you this, right? I'm going to give you that, and you're going to need to know that that's log base e so that you can immediately do this. Otherwise, you're going to be freaking out saying, I need a calculator. I'll be like, no, you don't. Right? Now, we're talking about this relationship between logarithms, logarithmic form, and exponents, exponential form, because there is a beautiful relationship among the two families of functions. If I look at an exponential growth function, again, the parent we know goes through 0, 1. So this is y equals b to the x. Exponential growth, in this case, b is greater than 0, right? If I take the inverse of that exponential function, graphically reflecting it across the line y equal x, guess what I get? The logarithmic function.
No way.
So by interchanging the domain and range, that's why I said the line y equal x is very important.
Oh, it's like, oh, because it has, there's the asymptote that's on the side, right?
That's right. So where is the horizontal asymptote for your exponential function? Your horizontal asymptote is here, right? For your exponential function. So where does that appear in the graph of its inverse? It is a vertical asymptote for the logarithmic function. Okay? We don't flip it, we invert it, we invert it, we invert it, we invert it, right? So that's why putting all these together is so important in understanding the relationship between a function and its inverse. It is the reflection across y equal x, but it is also the interchanging of the domain and the range values. So if I ask you to graph a logarithmic function, if you can convert it to an exponential function, you can create a table of values. You don't need a calculator. You could graph it. Graph the exponential function, then take those domain and range values, interchange those ordered pair values, get the ordered pairs for the inverse, and then just connect it. It's that easy. Okay? So the domain of a logarithmic function is what? What is the domain of every parent logarithmic function?
No, it's
No.
0, not included infinity.
Yes, thank you, Josh. Jonathan, nice try, right? Because we have a vertical asymptote at x equals 0. So the range of a logarithmic function is what? All real numbers, right? Because we're thinking back to its inverse, the exponential function, who has domain all real numbers, but range 0 not included to infinity.
That means that the parent exponential
Well, what does it mean for it to be 1-to-1?
or
Linear. Constant.
Oh, what does it mean for a function to be 1-to-1?
Quintic, linear. Exponential.
Inverse, it's inverse.
It passes the vertical line test and the horizontal line test. So the original function, as well as its inverse, is also a function.
Oh, you were talking about
Even though
41 out of
it might
80
be a
on that
relation,
test.
but it's not.
Right,
Does that
right.
mean the inverse never
I was a
intersects?
61 though.
No, they still.
They could intersect. Yeah, because it depends on where the points fall on the line y equal x, right? If they're on y equal x, those points don't change.
It just means that the inverse
Will be a function. Yes, yes, yes. Okay, so let's talk about how you would graph this logarithmic function. So let's say I give you this, and I ask you to graph it, and you're like, oh, heaven, help me. Well, if you know the relationship between an exponential function and the logarithmic function that corresponds to it, its inverse, I could just rewrite this as 2 to the y equal x, but then, we like to graph in terms of y and x, so we'd have to interchange the domain and range. I could just plot table of values for this. And do I have any domain restrictions on this? No, so I could pick anything. I don't care what you pick. What do you want to pick? What points you want to pick?
one.
Can we maybe go from least to greatest in terms of x?
Yeah, -4.
Okay, I'm going to just do -2. Y'all make it this way too hard. You pick whatever points you want, but those are the ones I want to see. Okay. So if x is -2 in this exponential function, what is y? 1/4, right? This is just 2 to the -2, which is just 1 over 2 squared, which is just 1/4. What about if x equals -1, what is y? Okay, what if x is equal to 0? Always, right? Every parent exponential function. No transformation, you're passing through 0, 1. What about if x is equal to 1? And if x is equal to 2? So I could graph this. All right, so I'm graphing that. -2, 1/4, -1, 1/2. So that's y equal 2 to the x. So if I wanted to know the graph of its inverse, I can just interchange my x and my y. So let me just erase this to not be yellow because that might be misleading. And now I'm going to graph that. How am I going to get it? I'm going to interchange my x and my y from my exponential function. So that means when I'm at x equal 1/4, -2. Do you see how I'm just interchanging my domain and my range values? And then I could plot those points. So when x is 1/4, I'm at -2. -1, I know I pass here, then 2, 1, then 4, 2. And there's y equal log base 2 of x, its inverse. Now, keep in mind for my exponential function, I have a horizontal asymptote at y equals 0 for my exponential function, but for my inverse, I have a vertical asymptote at x equals 0, right? So all you have to do is look at the corresponding inverse, graph it, interchange the points, and you have your logarithmic function. Does that make sense? That's the quick, easy way to graph these. Now, can we apply transformations to these? You bet. And you have to perhaps think back to the exponential function. What would the transformations be for the exponential function, and how would that affect the graph? So let's go back to this original one before we answer these questions. If I take this exponential function, the original exponential function, and I shift it up. So if I wanted to shift this up, I would be adding a number here, right? If I were to reflect that vertically shifted up exponential function, what do you think it's going to do to the inverse? What is it going to do to this logarithmic function?
Shift it to the right.
Shift it to the right. So how would that be represented in this equation? Do you see that relationship, right? Isn't that what it means to shift something to the right? Do we see that relationship?
So would
Okay, so let's go ahead and talk about that. What would happen if I then took this exponential function, but now I shifted it to the left? If I shifted it to the left, that means I'm coming up here and adding a number, right? If I'm shifting it to the left, what do you think is happening to the inverse? It is moving down. So we have to be able to recognize those relationships.
But isn't it like, so for like log 2x,
2 to the x.
what?
2 to the x. You said 2x. That would be linear. 2 to the
Log
x is x
2
to the x
to
power.
the x.
Uh-huh.
Yeah. Wouldn't that just be 2 to the power of y equals x?
Yeah, but then since it's an inverse, we're interchanging the domain and range, and that's why it becomes, the argument is still x, right?
How do we, does it never states it's an inverse?
Well, but I'm just now explaining to you that the inverse of an exponential function is its corresponding logarithmic function. That's the relationship between exponents and logarithms. So if I look at these, this is your parent, right? And you should be able to do a quick sketch of the parent. So that's this, right? With a vertical asymptote here. What have I done to this parent?
Shifted it down one.
I've moved it to the right one.
Oh,
Come on, Josh.
Come on, Josh.
Come on.
Does that make sense? This is now moving it to the right one. What has this done to the parent? It shifts it down one. Right? So again, you should be able to recognize transformations made to any function, whether it's exponential or logarithmic. Now, we're going to talk about properties of logarithms next week, but I do want to review one thing. Let's go back to this table that some of you did and some of you didn't complete. I just want to reinforce, for example, how to do exponential functions if you read it. Now, what should we recognize if it is an exponential function? A constant ratio, right? A constant ratio. If it's exponential, which this one is, there's a constant ratio. So 32 divided by 16, 16 divided by 8, 8 divided by 4, 4 divided by 2. What is the constant ratio? 2. Okay, so if I'm writing the rule, where does that appear? That appears to the base of your exponent. But remember, there's a little a value in front. Where do I get that a value?
Y equals 1x equals 2.
There's my rule. It's that easy. Okay?
Is there any way to tell C or D from the table?
What is C or D?
Well, the parent function is a.
For an exponential function, it's y equal a times b to the x. That's your parent, right? B is the constant ratio. A is the y value of the y-intercept, your initial population. Now, that constant ratio 2 that we got is by looking at the constant ratio if our inputs are consecutive integers. If I had skipped every other one, I'd have to divide it by 2. If I skipped every third, I'd have to divide it, right? So that's for consecutive integer exponents. Any questions on this? Okay, put everything away. Those of you who are online, I'm going to post the pop quiz online. I wasn't kidding when I said pop quizzes every day for this fall. I did at the beginning of the year. Put everything away. This is non-calculator, non-calculator,
What's the first pop quiz I've had?
non-calculator.
What's this on?
That's like when your English teacher says you're gonna have vocab every week. It never happens.
I told you at the beginning of the year that for logarithms, I give a pop quiz every day,
Every day?
every single day.
Wait, what?
Is this about what we just learned?
No, this is over what we did last week.
Every day?
Yeah, it's graded.
What did we learn last time?
You roll.
Everything goes away.
Yeah, they were closer a couple of days ago. That's a fun.
I told you to
Wait,
spend a long weekend
So
doing
next
that.
class, we're gonna have a pop quiz?
Yeah.
Every class. Every class.
Is it just in general that
It's on
everything-
logarithms. Logarithms, once you get it, it's super fast and easy. If you don't get it, it kills you. So I'm not gonna let it kill you.
Dios mío.
It's a lot of fun.
Put it away, put it away, put it away. Okay, those of you online, I'm posting it right now. You will do it on a paper or you can, and just submit it. So let me post it. It's coming. Those of you online, can you see it in Canvas under assignments? It's called Pop Quiz 4.1. Mia, Ethan, Catherine, Ava. Do you see it?
I don't see it, but
No, I don't see it.
Okay. Refresh. Do you see it now?
I still don't see it.
Yeah, I found it.
Okay.
Oh, just kidding, I see it.
Okay, good.
Are we like doing it on paper and then scanning it?
You can do it on paper and scan it, or you can just write your answers down on a sheet of paper, a blank sheet of paper, and submit it.
Okay.
Because, I mean, it's real fast.